Hello, and welcome to Chapter 6.2, where we will be talking about how to use simulation to compare two group means. Just as a review, we used a 3S strategy, where the S's are statistic, so we compute our sample statistic. Simulation, we conduct a simulation to explore what our sample statistic would look like under random chance. And 3, we use our simulation to assess the strength of the evidence that we have from our sample about whether this is likely to occur under random chance. This time, our hypotheses are going to concern mu1 and mu2. And just like in Chapter 5, we care about the value of the difference between those two group means. We are interested in the long-run value of the difference between the means of the two groups. So that corresponds to either data collected forever and ever and ever, or the quote-unquote true value of the population difference in the means. But either way, our null hypothesis is going to be that the two groups are the same, which can be written mu1 equals mu2, or equivalently as mu1 minus mu2 equals 0. Along the lines of mu1 minus mu2 is not equal to, greater than, less than 0. That is basically the same as in Chapter 5, except that there we had pi 1 minus pi 2, and we're working with proportions. Now we have mu1 minus mu2, and we're working with group means. But more or less the same difference. So to simulate, we take all of our values and we assign them new group labels. Because if the groups are the same, then it doesn't matter which group labels are attached to which values. Our statistics value should be the same, right? For those of you who were around for the last day of in-person class, you remember I had some index cards that I shuffled and then physically sorted into groups. Here's the virtual demonstration. My Photoshop skills were, I lost any sort of patience, I guess, in creating more than 3 cards per group. But we have our two groups, we have them in 2 stacks, and we compute the average value of each stack. So in this case, we've got the average value of each group in our sample, right? And if we want to simulate, we shuffle. So we shuffle the 2 sets of cards together and then deal them back out so that there are the right number of cards in each stack. We label the stack on the left simulated group 1. We label the stack on the right simulated group 2. We compute the mean of each stack, subtract the 2 means, and that is our simulated statistic. Then we do it again. We reshuffle, redeal, calculate the means, subtract them, get a new simulated statistic. And we do that again as many times as it takes. So in each simulation, we are simulating an entire experiment, an entire set of values. Each time we're assigning new groups to the outcome values that we actually observed. In a simulation, our null hypothesis is that the mean measurement, right, is the same in both groups, whatever that measurement may be in the context of the problem that we're working on at the time. One repetition involves re-randomizing groups for each of the observed measurements. And our statistic is the difference in the 2 simulated group means. I'm going to apologize for not coming up with an example that's more fun than the one in the book, but really I just like saying didgeridoo. It's a fun word. Fun instrument. So, evidently, some scientist got a didgeridoo and started taking lessons and noticed that his sleep apnea improved. He was intrigued enough that he set up a study with 25 people, randomly assigned 14 of them to receive didgeridoo lessons, and the other 11 were part of the control group and presumably found other hobbies to take up their spare time. After 8 weeks, the difference in their Epworth scale sleep apnea scores were recorded for each individual. So we have initial measurement, we have post measurement, but the data that we actually record is the difference between the two. What this means is our two groups are control here that did not receive didgeridoo lessons, and then the didgeridoo group who received lessons. The vertical line in each panel is the group mean, so that's our simulated statistic, or at least the difference, scratch that. That's our observed sample statistic, or rather the difference in the two means is our observed sample statistic. Our groups are the treatment or control, so lessons or not. Our response variable is the difference in sleep apnea scores after 8 weeks of lessons or not. We set up our null hypothesis, so that would be mu didgeridoo minus mu control equals 0. The two groups are the same. The didgeridoo lessons didn't change anything. Our alternative hypothesis is that the didgeridoo lessons increased the change in the Epworth scale score after 8 weeks. So that is the magnitude of the change after 8 weeks is bigger in the didgeridoo group than in the control group. So the difference is greater than 0. This experiment used random assignment, which means that we can conclude that the treatment actually has a cause and effect relationship with the response. So I made a animation of what 100 simulations look like. In each simulation, you can see that there are assigned groups, so that's the different plots, and the points are still colored by the original group membership. So you can see that each group is a mix of observations from the control and the treatment group. In our 100 simulation trials, there were no trials that showed a value as extreme as what we observed in our sample. We can't say our p-value is 0 because we didn't run infinitely many simulations, but we can say that p is less than 0.01, and that's enough for right now. So our p less than 0.01 means that we can evaluate the strength of this evidence. With a p-value that small, we have very strong evidence against the null hypothesis that the two groups are equal. We reject the null hypothesis and conclude that didgeridoo lessons cause sleep apnea scores to decrease relative to individuals who did not have didgeridoo lessons for 8 weeks. We can conclude that there is evidence that didgeridoo lessons reduce the symptoms of sleep apnea. All right. Complete on your own or in groups, complete exploration 6.2, questions 1 through 15, and upload your results to Canvas. If you work in groups, that's fine. just put everybody's name on the assignment and turn it in only once so that Josh only has to grade one assignment. We want to be kind to Josh. And if you want to make use of Canvas groups to collaborate, send me a message as to who you want in your group, and I will do my best to set that up. So, I hope you are all staying safe and healthy, and I'd like to remind you that if you have questions or any sort of confusion that you'd like me to clear up on any of this material, please make use of the discussion board on Canvas. Your classmates probably also have similar questions. That saves me from answering the same Canvas messages over and over and over again. It also benefits people who are maybe too shy to ask. Don't be that person, but if you are, that's okay. Let's just try to everybody help with maintaining some semblance of class community, even though we're scattered across the state, the country, the globe, I guess, at this point. So, I hope you guys have a wonderful day, and I hope you're making the most of this self-isolation stuff. So, talk to you later.